Hello and welcome to this video. In this video we're going to make a start on the topic of electric fields. So we've already looked at gravitational fields, we've seen how forces, electric field strength and everything behaves in a gravitational field. Now we want to convert all of the knowledge that we know and see, is it the same, is it different, what changes if we're now going to look at electric fields. And for the most part I can tell you in advance that mostly we look at the same kind of principles. We'll always end up with similar expressions for things like the force, the field strength, the potential. These will all be pretty straightforward and similar. The only difference is that actually the force that we're working with is no longer gravity, we're actually now working with the electromagnetic force. And we know from particle physics, the electromagnetic force acts on charges, not on masses like the gravitational force does. And actually what we find is that a lot of these equations are going to be similar. But what we need to do to start with is go back to how would we draw these field lines. That was the first thing we did in gravitational fields. So we're going to follow a similar structure and let's look at field lines. Now we said for gravitational fields that we can have two approximations. We can either make the approximation that this thing is a point mass, in which case we have a radial field, and we're going to do the same for electric fields. We're going to say this is a point charge. Now the only difference here is this point charge can be either positive or negatively charged. So I'm going to say this is a plus Q, so this has a positive charge, and the radial field lines will follow a very similar type of shape. The problem now is, what direction do they point in? We said for gravitational field lines that they will always point in the direction of the force, which always goes towards the center. But now if I put a positive mass in here, it's going to go away from this. So if this was a positive mass in here, it's going to get pushed away. And if it's a negative mass, or sorry, positive charge or negative charge, when it's negative, it's going to get pulled towards. So we don't actually know what which direction these are going to go in unless we choose one of them to just be the convention. And that's exactly what we do. We choose that whenever we're doing things for gravitational fields, we said it was always a test mass. In this case, we're going to say it's a positive test charge, which means that the field lines will always go from positive to negative. So always from the positive side to the negative side. Okay, which means in this case, if I have a positive charge at the middle, these are all going to go away from this field. And in the same way as we did in the gravitational fields video, we have boundaries to this, because we also know from the electromagnetic force in particles this has an infinite range, which means that these field lines never actually come to a stop, which means we have to put some boundary around it, because these field lines will only ever come to a stop when they reach another charged particle. Okay, and specifically in this case, where I'm starting with a positive charge at the center, they will only ever stop when they come to a negatively charged particle. But this is our example of a radial field. Okay, now we said this was one example when we treat this as a point charge, but then the second example we had in gravitational fields was we said we can have uniform fields. But we said that was an approximation for gravitational fields. It's not actually possible to create a gravitational field where it's a uniform field. It's an approximation we make based on how close we are to the field. However, in the case of electric fields, it is possible for us to get uniform fields. And the way we do that is to create a pair of parallel plates. So these are just metal plates, and we'll just attach one side of them or both sides of them to some sort of battery that's going to provide some sort of potential difference between these two, where one plate is going to become positively charged because all the electrons get pulled away into this wire, and then this one becomes negatively charged where all the electrons have come towards it in this wire. And actually the field lines here will be uniform field lines. Okay, so they will just go from top to bottom, and now they always have to be from positive to negative, so they will go downwards. Okay, and this is a uniform field. So we can form uniform fields now. This is possible. There is kind of a little bit of a extension when it gets to the end. You're going to start to see some sort of curvature, but for the most part you can just assume that the points on the end are negligible in comparison to the points in the middle. But for the most part this is a uniform field. Now we need to look at how would these charges change, or how would the field lines change if I were to now have a multiple bodied system. This is if I have just one charge here. What happens if I get two charges? Okay, well, if I have two charges, the first case is that they are the same charge. Okay, so it doesn't matter in this case whether I choose them both to be positive or negative, because the field lines will look the same, the arrows will just be in a different direction. But I'm going to arbitrarily choose them to be positive. So if I decide I have a positive charge here, and then I'm going to have another positive charge here, what we said for the gravitational things is that it will connect in the middle, and then all lines will try and connect to this charge as much as possible. However, we know in gravitational fields everything is attractive. That isn't the case in electric fields. If we have two positive charges, they're never going to be attracted to each other. We're never going to get the field lines pulling them together. They're always going to push them away, which means actually the field lines here can never touch. They can never meet because their whole point is to push each other away. So what we actually see is something similar to gravitational fields for these parts, where on the outside where it's pointing away from this it's okay, but when you get closer to it, these will actually begin to diverge. So they never actually come in contact with each other. And all the field lines always point from the positive to the negative, so it will be going away in all of these. If these were all negative, all of these arrows would be in the opposite direction. And these ones will also be going away from this positive charge. And I would also have to draw a boundary around this. But this is what happens when you have like charges, because like charges repel. Okay, this should be very familiar, but if I have two charges where they're opposite, so I have a positive and a negative charge. Let's say I have a positive charge here, this is plus q, and I have a negative charge here, this is minus q. There is now attraction, so it will look the same as the gravitational field lines did. We're going to have this kind of effect where the field lines want to attract these two together, and then we'll end up with some excess field lines that are pointing in the other directions. And now all the field lines have to go from positive to negative, so these are going away from the positive towards the negative. And this is when we have opposite charges, because they attract each other. Okay, so this gives you a brief idea of how these electric fields are going to interact. When we have radial fields, they will have this kind of situation where they can either repel or attract. Now this means that we're either going to get forces that are going to push outwards or inwards. We're going to have to be more careful in the forces video when we look at the direction of a force. But I briefly mentioned this idea of a positive test mass, or positive test charge in this case. So let's go through what I mean by a positive test charge. So this positive test charge is just a conventionally, so this is just something we've chosen to do just as the convention, because if we didn't, then some people would treat it as the field lines would point in the wrong direction to other people, or the other direction to the other ones. So we conventionally just decided as a collective to say that we are going to treat this as if there's a positive test mass. We evaluate all variables, so force, field strength, potential, based on what a small positive test charge negative test charge feels at that point, or at that position in the field. Okay, so in general, the same way that we treated gravitational fields as having a test mass, we know the mass has to always be positive, but now we have to define whether we're doing a positive or negative charge. So now we need to make sure that we're defining this as a positive charge so that all conventions line up, and we know whether there's going to be forces of attraction, we know what direction the field lines are going to go in. It's all based on this idea of the positive test charge. So hopefully all this makes sense as an introduction. Hopefully you can already see the similarities that are going to arise between electric fields and gravitational fields. Thank you for watching.